Okay, so I did a talk a couple of days ago on lean and high energy physics, and I thought I would record it, put it online, so anyone that can watch it can. Anyone that wants to watch it can. I guess there are two types of people that are going to be watching this. There is somebody that perhaps knows what lean is and doesn't really know what high energy physics is. If that's you, high energy physics is basically just particle physics. It's things like GR, things like particle phenomenology, the sorts of experiments they do at the Large Hadron Collider. If you're a high energy physicist and you have no idea what lean is, hopefully this talk will tell you what it is and what this project HepLean that I'm working on, that I'm having, or that I'm developing, is all about. So I'm not actually going to talk about really lean until about the second half of this talk. I want to start with some motivation. And that motivation is to give you 4 problems with high energy physics. So this is not 4 problems in high energy physics. This is 4 problems with high energy physics. But before you think I'm going to be putting on my boxing gloves and, beating down my own discipline, that's not what I'm going to be doing. I'm going to give you 4 problems, and then in the second half of the talk, I'm going to give you a solution to those problems. I don't think the problems that I'm going to give are particularly controversial. Feel free to disagree with me. I'm happy to hear opinions thereon. So the first problem is that there are mistakes in papers. And these mistakes can be, for example, a typo, or they can be things more subtle, like a definition that's wrong, or a mathematical proof that, it kind of is correct, but it's just kind of missing a step that means it's wrong. So there are probably countless examples of this on the archive. And even more worrying is that there are probably a bunch of examples of this in peer-reviewed publications. So here's a specific example. This is from one of my own papers, and this was already published in a journal, or rather this is published in a journal. So despite me and my 2 co-authors looking at this paper, a reviewer looking at this paper, and then the people that proof the paper and make it look pretty from the journal, despite all of those people looking at it, a typo still managed to get through. There is a minus sign missing in this part of the equation. Doesn't seem like a big issue, but if you think about it, or think about yourself and ask yourself, have you ever been in a situation where you spend a lot of time trying to work out, what sort of, reading the paper, you're trying to work out an equation, you're trying to work out what it says, and then you realize actually there's a typo, there's a missing minus sign, or there's a missing factor of 2 there. Maybe it hasn't happened to you, but it probably has happened to somebody that you know. So problem number 2. So as a field, we're not really set up to reap the benefits of artificial intelligence. And by this, I really mean the way that we write papers is such that if the paper was written by artificial intelligence versus written by a human, we actually care about that, from the simple fact that artificial intelligence produces things that looks correct, and it's very hard, unless you read closer, to determine if it is correct or not. So on the screen, I've written 2 examples. One of these is an abstract from one of my papers, and one of them is a AI large language model generated version of the abstract. So that you don't have to read it. Don't feel pressure to read them in full, but basically the top one is generated by AI, and to actually see that it's wrong requires a bit of thought about what it's saying. It's not obvious. And in this way, as a field, we're not set up to, use AI to prove results, to do calculations for us, because we keep having to do this check and we have to make sure it's right more often than not. It's not right. And so we can't use AI perhaps to the benefit that some other fields can. So that's problem number 2. Problem number 3 is the following. There are vast amounts of papers out there for high energy physics, in high energy physics, which collectively store information in a non-linear fashion. So I put a screenshot from Inspire HEP, and as you can see, there's over 1,200,000 papers in high energy physics alone. And the way that we do high-energy physics is that somebody publishes a paper over here on like a subject, and then somebody might produce a paper over here, and then someone might produce a paper over here, and they may be connected, but this one might be connected like to this one, and this one might be connected to the one over there and there. And to find the information, to sort out that information is very difficult. It's not like a text, it's not like a textbook. So in the textbook, it's often a table of contents. You look at the table of content, you go, okay, I studied this, and now the thing that I want to know is it will be in this section because it's just the broad area, and it will be in this subsection, and so on and so forth. So high-energy physics and papers, and the way that we produce papers, is just not like this. Which means that the lookup time for information in high-energy physics is long, and then sometimes it becomes very difficult. I suspect that most people watching this video have been in a situation where they've spent some time trying to work out, maybe do a calculation or trying to work out a theorem, to realize that that has been done before, perhaps 100 times in a bunch of rapid papers. So that's problem number 3. Problem number 4 is kind of somewhat different to the other ones in a sense. It's that there are coding errors in high-energy physics. So most high-energy physicists use something like Mathematica. Maybe they use like Monte Carlo simulations, event generators, basically code that people have written. And depending on how long the code is, there could be minor sign errors. There could be other sorts of mistakes in there. And often these are hard to spot. Sometimes they waste time because they actually take like years and years to spot, to realize that's actually a mistake in these code systems. And they can lead to results which are just incorrect. So that's problem number 4. And I have an example of this, is that one of my recent papers, I wrote a Mathematica script with a bunch of colleagues, or with 2 colleagues, to classify semi-simple extensions of the standard model. This Mathematica script was like 2,000 lines long, and there's very likely a mistake in there. I don't know that if there's a mistake in there, but there probably is. I don't think you can really write 2,000 lines without there being a mistake. Whether that mistake is, vital to the conclusion of the code is different or not, it's different, but we just don't know. So there's this like ambiguity there of whether, is the code right or is it wrong? Is it producing the thing that we actually says it produces? So yeah, and this leads to waste of time. So they're my 4 problems. Hopefully they're not, super contentious. Hopefully you're not like writing me an email going like, no, this guy, he's saying all of these problems with high-energy physics. I'm not doing that. I think these problems are, hopefully you'll admit that they exist. They're not major problems, but they are problems. So why give you problems? I give you problems because I have a solution. So let me first hint at a solution. I don't want to, waste my talk straight away and give you the solution. I'm going to tease you a bit by just giving you a hint. The hint at the solution, as you could probably guess by the title of my talk, is this thing called HepLean. So HepLean is a computer program developed by Microsoft. So that's the first fact you need to know about HepLean. It was a computer program and it's developed by Microsoft. Here is an example bit of code for HepLean. So this bit of code, if you're a high-energy physicist, defines the anomaly, the gravitational anomaly for the standard model plus 3 right-handed neutrinos, or for the N family standard model with 3 right-handed neutrinos. So let's see if I can get my mouse to show. I cannot. That's a shame. So the first bit of this code, this toFun bit, really defines the gravitational anomaly. And below that, you have a proof that this function is linear with respect to addition. And the second bit is a proof that this function is a base scalar multiplication. In other words, that this function actually defines a linear map from the vector space of charges of the standard model to the rational numbers. So this kind of looks like something that you'd write in LaTeX, right? It's a definition, it's a proof of some properties of the function, and then beneath that I've written a lemma, which is just a different rewriting of the gravitational anomaly in the standard model. So this looks like something you'd write in LaTeX, right? It looks like something you'd see in a paper. But it's slightly more than that, because Lean is not LaTeX. Lean has a special property that LaTeX doesn't. And this is vital to how it forms a solution to the problems that I've said. Lean will only compile if what is written in it is correct. So that definition on the slide, that this map is a base scalar multiplication, or the proof rather, that this function, a base scalar multiplication, and forms a linear map, is correct. There's no ifs or buts, there's no errors in that. The computer checks it for you. And this allows you to write stuff in a way which is, which is correct, because there are going to be no mistakes, because Lean won't let you produce the output, it won't let you produce the paper, the PDF in a sense, unless it's correct. It won't compile if it's correct. Before I go any further, you'll notice that I put a link on the slide. The second half of this talk, or the very end of this talk, I'm going to do a demo of Lean. If you want to follow along that demo, you just need to follow that link. I will put a QR code on at the appropriate time, on the screen at the appropriate time as well. So Lean is this amazing thing. It produces stuff that looks like maths, it looks like physics, it looks like the stuff that we write in papers, but it has this extra property that it can be checked by the computer. So to give it some example uses, Lean has been used by the mathematics community to write down a lot of mathematics. They're trying to write down the whole of the undergraduate mathematics curriculum in Lean, and this shows just how versatile it is. So on the screen, on the top right diagram, this is the GitHub repository called MathLib4, and it contains all of these definitions of theorems in an organized way. So each of these directories, for example, the category theory one, contains files and files of things that look like this, with definitions and lemmas and theorems about category theory. And if somebody wanted to prove something about category theory, they could open that file, they could look at the definitions, they could use those definitions, they could use the theorems in their own proofs in a very easy, natural way. They don't have to prove stuff again, unlike perhaps what would happen if you use Mathematica and you were trying to prove something. It's quite hard to, take that proof and use it somewhere else. In Lean, it's completely doable. So that's use in mathematics. There's also use in chemistry. So there's a collaboration at the University of Maryland, or a group at the University of Maryland, led by Tyler Josephson, who is looking at using Lean in chemistry. So this is an example of Lean outside of the realm of mathematics, outside of the realm of, in the realm of physics, much closer to what we want to do as high-energy physicists. So let me give you the solution to those 4 problems. The solution is to form a GitHub repository written in Lean for high-energy physics, containing definitions, theorems, calculations, perhaps experimental data as well, written in Lean, so that it can be used, or so that we can have this database of results that people can use to make the database bigger, basically a collection of knowledge in high-energy physics. Something like MathLib4, but for high-energy physics. So how does this solve the problems? The first problem was that we have mistakes in papers, and I've already explained how this solves it. The reason this solves it is that Lean will only compile if it's correct, which means that everything you write, everything that would be put into this repository, would be by definition, or not by definition, but it would be computer verified as correct. So there will be like no mistakes. You won't be able to use a theorem that's actually incorrect. And this would be a great benefit, because it will stop people like wasting time of, using results that are incorrect, or which have minus sign errors or factor duress. Problem number 2 was that we're not set up for artificial intelligence. We're not set up to AI. The solution, how this GitHub plus Lean solution solves this, is that if something looks correct in Lean, it is correct. There's none of this issue that I was talking about before, about like a large language model producing something that looks like, what we'd write in a paper, and you have to worry about if that's correct or not, because You know, large language models are very good at looking correct, but they often don't reason about it. If something looks correct in Lean, and if Lean tells you it's correct. So this means that you could get artificial intelligence, you can get AI to start writing proofs, to start writing definitions of things in high-energy physics. And if those are correct, the computer would tell us. We don't have to worry about, you know, breaking it down to see if it's correct or not. And this is we're already at the point where artificial intelligence can be useful in this regard. So GitHub Copilot, the interface of GitHub Copilot with Visual Studios, which is the main programming suite that people write Lean in, it's already very good at proving very simple theorems. So if you have a very simple theorem that you want to prove, often AI can already do that for you. You don't have to do it manually. And you don't really have to check the proof if you don't want to, because it's correct, because Lean tells you it's correct. So problem number 3 was this thing about the fast amounts of papers and the nonlinear storage. So really, we would use the power of GitHub to do this, using GitHub's workflow systems, its continuous integration, to allow for an easy way to linearly store information in high-energy physics, basically storing things in the correct directory, making sure it's all nice, it's all syntaxed correctly, so that you have a repository that can be used by other people, by the community, really, without much thought, without much, you know, having to worry about the individual components. They can really just work with the definitions and the theorems that they need. So problem number 4 was coding errors, things like minus sign errors in Mathematica. And this is really where another reason where Lean is different from LaTeX. Lean is executable. That means you can write a function in Lean, and you can write a function like f of x equals x plus 1, and in Lean you can write f of 3, and it will tell you the answer of that is 4. It can actually execute code. So this LaTeX can't do that. You can't. I mean, it can, but much more difficultly. But Lean you can actually write code. You can write functions. You can do things that you might be familiar with in something like Python. And this means, or more like Mathematica is probably the better analogy, which means you can check results, you can prove results, you can actually do calculations in Lean, which could be used in conjunction with Mathematica or to replace Mathematica. So it could be used in conjunction to, you know, check the results and to catalog the results, to put that in the database for results, or it could be actually used as a replacement of Mathematica to do the calculations itself. So that is how the solution solves this problem. So where are we? You know, this is not just up in the air. We have made steps towards a solution. So that there exists a repository, which is this here. It's called HepLean. Hep has a capital H and lowercase e and a lowercase p. That is a coding-ish thing, rather than me not realizing that Hep is usually written with a capital E and a capital P. It just became easier to do it with a lowercase e and a lowercase p. And within this repository, I've already collected a bunch of results of anomaly cancellations. So I basically created a file and started to put the results from high-energy physics in this area of anomaly cancellation into this repository in a way which is, you know, not necessarily focused on one paper, but tries to cover the field in a broad way so that it's more easy for people in the future, if they want to do anomaly cancellation, to use the stuff there. So if you want to learn more, go check out the repository, go check out the code there. By the time you watch this video, I may have put other code for different areas, or other people may have contributed to this. And I actually think this is important to note. This project is kind of not a single paper. And the idea of what I'm doing here is more like perhaps a research program. So if you really want to get involved and you want to start writing stuff in high-energy physics in Lean, please feel free to contribute to the repository, add to the repository. There's details there about how to add to it, how to write in Lean, what areas of high-energy physics, you know, any input from the community, any help from the community to build this repository would be great. Okay, so let me give you a demo because this it's all very, me telling you lean is this magical thing. But I want to give you a demo of what lean actually is and what it's all about, and to show you lean in practice. So I have two QR codes on the screen right now. The one on the left will take you basically to this web address, or hopefully you can see my mouse now, sorry. Will take you to this web address here. That will give you a blank lean template, and you can follow along what I'm doing. Or if you want to cheat, you can follow this QR code to the final script, and that will give you basically what I'm writing now. So let us go to lean. Let me just close these tabs. Okay, let's ignore that. Pretend I didn't do that. I was looking at the CKM matrix over. So we want to prove a theorem in lean. So the first one we're going to do is we're going to import mathlib.tactic.polyref. So let me zoom in a bit, and hopefully I am not covering the screen. But so this is obviously a web interface to write lean in. If you want to write lean properly, you probably want to download something like Visual Studios and do it there. But this is a good place to learn. So this import mathlib tactic polyref. So mathlib is that big directory of mathematics results. Tactic is a tactic, and polyref is something to do with linear algebra. Don't worry about it too much. But this basically imports all the necessary linear algebra stuff that we're going to need to do this little tutorial. So we are going to prove a theorem, and that theorem, I'm going to call it the free fermion theorem. Okay, I'm not sure if that's spelled correctly, but if it's not, hopefully people can forgive me. So I'm going to prove a theorem that if you have free fermions charged under a U1 gauge theory, so they have charges A, B, and C, and that if those charges satisfy the anomaly cancellation conditions, which is that A plus B plus C equals 0, and that the cubes of those numbers put this on a new line, then we have the A equals 0, or B equals 0, or C equals 0. So notice that when I'm typing, if I want to write or, I'm doing /or, and then do a space, and that will do that. And for this Q, it was /Q, and then a space. So yeah, so we want to prove this theorem. This is basically the statement that if you have free fermions charged under a U1 gauge theory, one of the charges has to be 0 if it's anomaly free. So I can put sorry there, which tells lean that I don't have a proof yet, and it just stops any random errors coming. We have this tactic state here. So this tactic state basically says that this thing here, this bottom line, is the thing that we want to prove. And this H1, H2 are the hypotheses we put in, basically the anomaly cancellation conditions. And we have these A, B, and C, which are rational numbers. So to prove this, the first thing we're going to do is we're going to go half H3, and we're going to show that C equals minus A plus B. Okay, and you don't have to do anything really complicated to do this. All you do is you do linear combination, and that will prove it for us. Basically, because this equation is solved by a linear combination of this equation here. So that can be solved like that. Okay, so that's step number 1. And as you can see, we now have that hypothesis in our tactic state. We now want to prove H4, and we're going to prove that 3 times by A times by B times by C is equal to 0. And the way that we're going to do that, so now we have to prove this statement here. The first one we're going to do is we're going to rewrite left H2. So that's going to replace the 0 that we have. So if I put my cursor here, you'll see that we had a 0 here. And then after, it's replaced it with this. And this arrow here was /L space. And that replaced that. And then we can replace, so we have this equation here for C. So we can rewrite H3, which will rewrite C in our goal with minus A plus b. And then really the thing that we have to prove is this here, but this is just a problem in ring theory. So we can just write ring and then that will solve it for us, which is very useful because you don't have to worry about, you know, expand and stuff. Lean does that for you. Okay, so now we're in this position. Our tactic state now has this additional thing, which is H4, and we can simplify at H4. And Lean is clever enough to know that if you have 3 times by A times by B times by C equals 0, that tells you that either A is 0, B is 0, or C is 0. So if you simplify at H4, you get this thing here. And now H4 is almost exactly the same as our goal. It's not quite the same, but if we write exact question mark, Lean will look how to make them the same. And it will tell us, if you can see here, it says exact or associative on H4. And that solves our goals. And we can move to sorry, and we get an error-free proof. So this is a theorem in Lean. And the fact that there's no like red lines anywhere tells us that this proof works nicely. And now you could use this theorem in other parts of physics. So you wouldn't have to, no one would ever have to prove this again. This would be in the database and you could just prove it. So that's an example of Lean. Let me go back to my slideshow. And to finish off, let me say that if you want to learn more, go to the repository. There's a bunch of resources there that I've linked to about, you know, how you can learn Lean, where to ask questions. There's a frequently asked questions in inverted commas, not really frequently asked questions, but it's more like, you know, questions that I think are important to answer when it comes to these sorts of things. So that's all in that repository. And if you really want to, if you want to contribute, it would be great. Contact me either by email or on Sulip, or just do a pull request to the GitHub repository. Yeah, and yeah, let me know if you have any ideas, questions, or comments. And with that, thank you for watching.